Hello interwebs, welcome to Let's Fix Computers, and probably board repair basics, I guess. So in this video we're going to talk about replacing components. So I've got quite a few videos on my channel now demonstrating me doing board repair, often by removing short circuits from boards. Which are often shorted capacitors and stuff like that. However, a lot of you have noticed that I have quite a habit of not replacing parts. Now, there's a reason for doing this. Firstly, it's important to bear in mind that I'm not a master myself. You know, I'm learning this as we go at the same time. I'm kind of just sharing my journey as I learn it as well. And for the most part, a lot of the time I've not replaced components because I haven't had the spares to replace them with. And you might say sort of, oh, okay, well just order one online. And it's like, yeah, you could do that. However, ordering single components online is really expensive for what you're getting. And when you're not 100% certain what to replace it with, you know, you might end up spending an inordinate amount of money and time obtaining the correct parts. Usually when I do replace a component, it's because I've managed to dig through my spares boards, because, you know, the boards on the wall behind me and various other places in the shop are all spare boards, and I can rummage through those and take bits off them to replace parts that have gone. So yeah, as I say, I selectively replace parts when I think it's required. So the things that we've got to cover in this video are how to identify components, how to figure out what to replace them with, where to get your replacements from, and also sometimes in some instances when you have to sort of realize the fact that you don't know what to replace it with, and can you just leave it off the board. So let's start from the beginning. This is the board that we saw in one of my recent videos where I demonstrated voltage injection, and we're going to be demonstrating on this board. Now, this board is a non-runner, so I can't demonstrate it in action or anything. But the thing is, that doesn't matter. The objective of this video is not to actually make this board work, but just to demonstrate how we can look at a board for which we have no documentation about and figure it out. That's the thing. See, when you have documentation, this is really easy. Like, for example, on MacBooks, MacBooks are very well documented boards. And what I mean by that is that the schematics and board view are very easy to find if you go searching on Google. And when you have schematics, you can easily look up what component it is you need to replace on the board. So with schematics, no problem whatsoever, easy peasy. However, a board like this, I don't even know what model laptop this is from. It's from an old Dell, I don't know which one. There's no way we're going to find schematics for this. So this is a really good example for how do we figure out what to replace and where. Right, with all of that out the way, let's get into it. So in the previous video, I rigged up a faulty capacitor on this board, and I'll show you where I put it. I put that capacitor here. You can see there's an empty spot on the board where a capacitor has been removed. So this is where our shorted capacitor was, and I removed it from the board, thus clearing the short circuit. And to all intent and purpose, this board would now operate as normal. So that is where that went. So this brings us round to our first example of what I'm going to show in this video. I'm making this up as I go along, by the way. I haven't scripted this, so hopefully it doesn't go on too long. So with this instance, we removed a capacitor from the board, but we don't know what its rating was, so we've no idea what to replace it with. Now, this one's actually super easy to figure out, because what we've got here, these are the high side MOSFETs for CPU vCore, and we've got a two-phase system. If I just flip the board over, here's the two inductors and the low side MOSFETs. So as you can see, we've got two identical buck regulators that are mirroring each other, going to the same output. You can see that the output from these two inductors are both connected together, and they go down to the CPU socket. So back on the other side of the board, as you can see again, we've still got that mirrored configuration on this side as well. So this one is actually really easy, because if we've got a missing capacitor here, we've got exactly the same capacitor configuration over on this side as well. Now, it's not mirrored, but it's symmetrical. So we've got big, small, big, small, big, small, big, small. So we can easily see that the missing capacitor here is going to be identical to this one here. So if we remove this one from the board and measure it, we'll know what capacitor we need. Now, measuring components in circuit, and by that I mean while they're on the board, is tricky. There are some components that can be measured in circuit and some that can't, and sometimes you'll get an accurate result and sometimes you won't. I could put my multimeter into capacitance mode to measure the capacity of this capacitor. However, the problem is because the capacitor is in circuit with a load of other capacitors, we're going to get the result for all of those capacitors in parallel, which could be something completely different. And by the same token, if I were to go into resistance mode and try and check the resistance of one resistor down here, so I can put my probes across this guy, and it says 185k, so it may well be a 180k resistor. But the problem is that if it's a higher resistance and there is another path around this resistor by some means, then we might be getting the measurement for something else, because obviously the power flowing between the probes of the multimeter is going to take the path of least resistance. So because we're in circuit, there could be another way around the component that you're testing that is of lower resistance. So this is the issue with testing in circuit. So to actually get any kind of useful results, we need to remove the component from the board so we can actually test and identify it. So I'm going to turn on my hot air station and we're going to remove this from the board. By the way, I want to take this opportunity to apologise for my squeaky chair. It's getting worse. I need to replace these stools. So once again, because I haven't done any work on this board yet today, I'm just going to give it a bit of a preheat with the hot air. I'm just blowing around the general area and just bringing up the temperature of the board. Alright, let's get this guy off. Oh, these are the wrong tweezers for the job. Okay, we knocked a load of stuff sideways. Can I fix that? No, I'll tell you what, I'll fix that when I put it back on the board. Okay, so we've got our capacitor off the board. Now these tiny little boys, these little brown guys, these are multi-layer ceramic capacitors. Very, very common all across. They are not polarized, so it doesn't matter which way around the capacitor goes, and they work by having lots of layers inside them. There are lots of layers that are built up like that, with this being one end and this being the other. And as you can see, there is an insulated gap between the layers. And so by increasing the surface area between them, you increase the capacity of them. And the typical failure mode is the internal surface breaks down. So at some point, the plates are touching somehow, which turns it into a wire. So we've got a short circuit where my finger is touching my other hand. And that is how this guy fails. So being a capacitor, I'm going to set my multimeter into capacitance mode. See the capacitor symbol there. And we'll just touch the probes on each end. This is kind of difficult on a very small device like this. Let's hope I don't lose it. And there we go. We've got a nice clear 100 nanofarads there. Oh, I've just slid off slightly. But yeah, so that is a 100 nanofarad multi-layer ceramic capacitor. Now, you'll often have seen with capacitors that they often have voltage ratings as well. Now, multi-layer ceramics, they do have a voltage rating. However, because multi-layer ceramics are typically fairly low capacity, their voltage ratings are often very, very high. So we'll probably find that these guys are good for like, well, the really small ones are like 10 or 20 volts. Then the larger ones will be 30, and then the big boys will be up to like 50 volts. So generally speaking, you don't actually need to be concerned about the voltage rating for a multi-layer ceramic at all. As long as you fit the correct capacitance, the voltage rating is going to be about correct as well. And the thing to remember is that with capacitors, the voltage rating is not how much power the capacitor puts out. A capacitor will charge to the voltage that is put into it. The voltage rating of a capacitor is merely what amount of voltage it can tolerate before it breaks. So for example, if you take a big electrolytic, you know, the big cylinder boys, that are often will have their voltage rating written prominently on the side. The reason why they have those voltage ratings is that those guys will have much, much higher capacitance on them. So However, these multi-layer ceramics, they don't really care about the voltage very much. So the actual capacitance is the bit that we care about. So it's a 100 nano capacitor. Another way of measuring it that you may have seen me use before in a video is this guy here. This is a transistor tester. And it's a very rudimentary bit of kit that you can buy on Amazon, eBay, etc., etc. And this is also good for identifying components, especially if you don't know what it is. So if you've taken this dude off the board and you don't know if it's a capacitor, we can put it on this and it will tell us. So I'm just going to put it across the SMD pads of this guy, and I'm going to press it down with a plastic tool. And if we turn this on, it should also identify it for me. However, I'll tell you in advance, this thing is not particularly accurate, so we're probably going to see a different capacitance. No, there you go, look, 102.7 or 8, so 103. So actually, we're not far off the mark with that. So something like this is also very handy for measuring components as well. However, keep in mind that your multimeter is going to be significantly more accurate than a device like this is. These devices can be calibrated. However, I've never figured out how to make the calibration work on this. I've tried a couple of times, couldn't figure it out. But that's another example. Okay, so we have a 100 nanofarad capacitor. That is what we blew up on the board and what we need to replace. So we could jump on somewhere like eBay and buy a single 100 nano capacitor. That's probably going to cost a ridiculous amount of money just to buy this tiny little thing here. Or failing that, if you're doing this for a living, if you're running a shop like mine and you're like, well, I don't want to buy a single capacitor every time I'm trying to fix a board, you know, how can I get a selection pack or something like that? Well, as luck would have it, you can buy just selection packs. So obviously, if you're running if you've got an established workshop set up and you know exactly what the common failing points are on the laptops you're running, like for example, a channel like Lewis Rossman, because he works exclusively on MacBooks, he knows all the common failing points on those MacBooks, so he can buy in packs of specifically parts that commonly fail. Whereas with me, I kind of just work on whatever comes through the door and try and figure it out. So how do I know what parts to buy? So I went on eBay and I bought this pack here. So it's 720 0805, which is the size code. I'll talk more about size codes in just a sec. 0805 SMD capacitor, assorted kit, samples kit, 36 values, yada yada. And it's got 1 picofarad to 10 microfarad capacitors in it. And this cost me £7.56, so that's like, I don't know, $9 or $10. That got me this pack here. So the size code for these is 0806, which is a little bit on the large size. However, the physical dimensions of the capacitor doesn't really matter as long as you can make it fit on the board. In an ideal world, I would also recommend buying an 0603 assortment pack as well, which I still need to do. I bought the 0805 pack, which is this, but I also need some 0603 ones, because this guy that we removed is an 0603. So if I show you the size comparisons here, let's go in for the big close-up. So you can see that the capacitor we've removed is actually a little bit smaller than the ones I've got here. I'm hoping that I'll be able to fit one of these bigger ones on the board for the sake of the demonstration. However, if I'd also bought the 0603 pack, then I'd have had the correct size. However, the physical dimensions don't really matter as long as the capacitance is correct. And because these ones are physically larger, they'll have a higher voltage rating, so it was a safer bet on my part. So as well as buying this capacitor pack, I also bought an 0603 pack of resistors. So I've got a whole assortment of resistors here. And as you can see, it's got the ratings all written on the back. So we've got everything from really small resistors to really high resistance resistors. So like most of these, I'll probably never use. But because I've got a huge assortment pack available to me now, which again costs less than $10, what I can do now is as I repair boards, whatever I need, I've probably got one in here. And if I start finding that I've gone through most of one of these strips, then I'll know that that's a really common value and I should buy more of just that particular value. So for example, 100 nanofarad, to my knowledge, that's a really common capacitor value. So what I would probably be inclined to do is to buy a pack of, I don't know, say 50 or 100 of them. And if I'm buying a pack of like 50 or 100 nanofarad capacitors, I can probably buy that for just a couple of pounds because I'm buying them in bulk. So because this pack is an assortment pack with lots of different sizes in, it's going to be overpriced. But the thing is, it was only $10, so I don't really care. And it means that just for one-offs, I've got a lot of one-offs in here. And once I know what common values I actually need, by monitoring which ones I'm using, I can order higher quantities at a lower cost of that particular value. So, with that in mind, let's find a 100 nanofarad in my assortment pack. Okay, so I've separated out a bunch of strips that look promising. As you can see, we've got numerical codes on the back to show me the values. However, the thing is, I don't know my codes off the top of my head because I'm a dunce and I'm new to this. Like this one down here is easy. We've got 1p, so that's going to be 1 picofarad. Likewise, if we look at this one here, 100, that will be 10 and 1 0, so that will be 100 puff. And likewise here, we've got 10 and 3 zeros, so we've got 10,000. And so 10,000, that will be 10 nanofarads, unless I'm mistaken. Now, because I'm a dunce, I'm going to look up a cheat sheet just to confirm that what I'm telling you is correct. So if I switch over to Google, I just typed in 101 capacitor here, and as you can see, here's a common ceramic capacitor tags cheat sheet. So if we look down this, we're looking for 100 nanofarads. So here's 100 nanofarads, which is 104. So that is going to be 10 and 4 zeros. So that's 100,000. So I was correct in saying that a 103 is 10 nanofarads. And then a 104, that's 10 and 4 zeros, so 100,000, will be 100 nanofarads. So here's our 1004 ones, so we should find that these are 100 nano capacitors. So we've got our replacement capacitor ready, but before we put it back on, let's just consider what these ones are doing, because you can do what's called a blind repair, where you just replace the component that went bang without having any idea what it does or why it's there. But it helps drastically to understand the purpose of components. It helps you diagnose, and it helps you make a judgment as to what you can put in and when. So what are these guys on the board actually doing? Well, again, this is our CPU V-core, so this is part of a buck regulator, or a two-phase buck regulator. So we've got two individual buck regulators here. And as you can see, we've got varying size capacitors on the input along here, and then we've got some big guys on the output up here as well. So these big ones are on the output, those are our bulk bypassing. So what that is doing is that when the CPU takes a gulp of current, it suddenly slams onto load and needs a load of power. While it waits for the buck regulators to wake up and provide more power, it's got a reservoir of energy in these capacitors to suck from. And the idea is that these guys can power that sudden peak current while the buck regulators ramp up to speed again, because we're working in the order of nanoseconds here. So these guys are providing our bulk bypassing. On the input, these guys, like these two big dudes here, these are probably doing bypassing as well, I would imagine, being the size that they are. However, these small guys, these are there's not enough of them and they're too small to be bypass capacitors. So what these will be doing instead is these will be there to reduce ripple. And what I mean by ripple is that when you have a power rail that is being powered by a switching power supply. So like these buck regulators, they work by switching the high voltage on and off rapidly. And then you get pulses of high voltage that are smoothed into a steady average low voltage. But the problem is, by doing that, by having all this rippling and this on-off oscillation, you create a lot of high frequency clutter. Although you've got a smaller voltage coming out the other side, that small voltage and your input are both going, they're sitting there oscillating, often with specific frequencies on them. And that frequency might cause unwanted behavior in the device that you're powering. It might upset something, it might throw something out of whack. A high frequency might translate into a steady lower frequency oscillation at the output or something like that. So what these capacitors are there to do are to reduce that. So if you've got a wave, a voltage that's going up and down, if you have a capacitor on the output that is the correct capacitance for that particular wave, as the voltage goes up, the capacitor will absorb some of that and bring it back down again. And then when the voltage goes low on the wave, the capacitor will discharge and nudge it back up again. So the capacitor is acting like a shock absorber. It's taking that rumble and it's smoothing it out by absorbing or releasing the energy as the oscillations happen. And obviously, because you might have various different frequency components on that ripple, you have different size capacitors there. So we've got small capacitors for taking out tiny little wobbles, and we've got some big boys for taking out the bigger waves in there. So once we've gone through this, we've smoothed out that ripple into a nice, smooth, steady voltage. That's the objective. And for that reason, that's one of the reasons why we've got multiple of them here. And these two small ones, that might be a 1 and a 10 pico or a 10 and a 100 picofarad. Then the larger ones could be a 10 and 100 nanofarad. Or we might just have two 100 nanofarads and two 10 picofarads or something like that. We could take more of them off to discover that if we wanted to, but it's not really relevant at this point. What's important is that the one that we're missing, we've determined to be 100 nanofarads, and we've got our replacement. So what I'm going to do now is I'm going to prep up the board to put our capacitors back on. So what we'll do, we'll add in some flux, and I'll add in a little bit of fresh solder just to prepare the surfaces, and then we're going to use the hot air station to put these back on the board. Right, we'll put this guy in. He's too big, this boy, however he will fit. And the size of the component doesn't matter. The reason why they're different sizes is just for ease of fitting everything in. However, the value is what matters here. So let's get the hot air station now. I'll just put my heat-proof mat back under. And because we're blowing on very small components now, I'm going to turn the airflow down on my hot air station so I don't blow them off the board. So let's turn that right down. And on this side, I knocked one of them askew. Oh, I need to adjust this. So we're going to warm those up, and we need to straighten that guy out and just flow this guy back onto the board. I'm going to move this guy out of the way for a sec. We didn't reach this guy with the soldering iron, so there's no fresh solder under him. There we go. So he was taking a bit longer to come up to temperature. There we go. That's a little bit wonky, but that'll do. There's no prizes for neatness in this, he says, straightening it again and making it worse. Pro tip, quit while you're ahead. Right, let's get the other one. There we go. And now I'll get my soldering iron and I'll just touch up both sides of those to make sure we've got a nice good connection. I need to move the camera out the way just so I can get the soldering iron in there. And there we go. So now we've replaced our missing capacitor. We identified it, we sourced a replacement one, and we put it on the board. And because we've got a replacement pack with lots of different capacitor values in them now, we've got more capacitors. So next time we encounter one of these, the chances are we're going to have one ready in the pack. And if we find that there's a pattern of very similar capacitors that are always missing, then we'll know which ones to order. So what else could we replace on the board? Another good example of this is the Lenovo Yoga 530 that I fixed recently. This had a shorted capacitor on the main power rail on the underside of the motherboard. And if we have a look at the video footage from it, you can see that there is a very visible power plane on this board with various capacitors dotted along it. All of these capacitors are likely there to reduce ripple and or reduce ground loop inductance. They're not all essential, and the laptop runs just fine with the dodgy one removed. However, the chances are all of these capacitors are of the same value, and I could have tested this by removing a couple of other ones and checking if they all had matching values. And with the multi-pack of capacitors that I have, I probably would have been able to replace it at this point. So what if we lost one of these big ones here? These big dudes, these are a different kind of capacitor altogether. These are polytantalum capacitors, and they are polarized, so they have a positive and a negative. So the multi-layer ceramics that we've purchased, those are no good here. I mean, as you by a basic size comparison, you can see these things are huge by comparison. So how do we know the rating of these? Well, again, if one of these guys went faulty, it would be quite easy to figure out what it is because, for example, if this guy died, we've got an identical one right next door to it. And we can look around the board for other ones. So this is NEJ, what is that? EJ8. So there's one duct right next door. And if I look around the board, oh, here we go. There's some more NEJ EJ8s. So as you can see, whatever the capacitor is, if it has a manufacturing code on the top of it, the chances are there's going to be more than one of them somewhere on the board. So you could desolder another one, and once again we can measure its value. But the problem is that measuring the value, we don't know what voltage rating it will have, and that's the tricky bit. We can measure its capacitance, but not its voltage rating. But the manufacturing code here actually makes our life really easy. What I'll do is I'm going to bash that into Google. I'm going to search for NEJ EJ8 and let's see what comes up. NEJ EJ8. And here we go. We've got tantalum capacitors. Cool. So what do we get from this? A very slow loading website. This is taking ages. I'm seeing if any of the other results are any good. What about this one? There we go. Now we're getting results straight away. So let's search the page for what we searched for. NEJ. Okay, we've got no results for NEJ. What about EJ8? Here we go. And there we have it. For this manufacturing code, the EJ8 denotes that it's a 220 microfarad capacitor rated at 2.5 volts. So now if I were replacing that, I would probably take one off the board and I would measure the capacitance to see if it's 220 microfarad, because that would confirm that the readings that I'm getting here are correct. And personally I would do that because I can. It's up to you if you want to do that or not though. I would, because then you can just confirm that the results that you're seeing actually line up. If you took one of these off the board and measured it and you got, I don't know, 120 microfarads, then that might imply that the information that you've looked up on Google is incorrect. So therefore the voltage rating might be as well. The other thing as well that you can use to sanity check the voltage rating is you could ask yourself, well, what kind of line is this on? For example, if we found one of these huge capacitors, if this is sitting on your V-in rail that's running at 19 volts, and you've got a datasheet telling you it's a 2.5 volt capacitor, clearly that's wrong, because a 2.5 volt capacitor, that'll blow up if you put it on a 19 volt rail. But then the other thing as well is that we can look at where this is. As you can see, it's on the output side of a buck regulator. Look, here's our MOSFETs, here's our inductor, here's the output, and it's going into something over here. Let's flip that over. Hey, look at that. It's powering our DRAM slots. So that's almost certainly the RAM power supply. Now, obviously our RAM, that's running at about 1.2 volts. So a 2.5 volt rated capacitor, that's completely reasonable. So we can have a look at this and we can do some basic, just common sense checks to see if what we're reading and what we're looking up online actually makes sense or not. So that's what we can do for the big boys. Now, what about if it's something like a resistor? Now, resistors, they don't fail that often on the basic ones. And if you're learning board repair, you're probably going to have trouble diagnosing boards where you've got bad resistors, unless you've got a literal exploded resistor in front of you. Personally, for me, most of the board repairs that I have successfully managed to do are usually the simple ones, like short circuits. Now, if you've got a resistor that has blown, resistors are often extremely small. Let's find one on the board. Okay, there's a couple over here. Now, as luck would have it, these resistors here, these are the little black squares around those capacitors, they've actually got their values written on them. That says 2R2, so that means 2.2 kilo ohm resistor. So we could easily replace one of those if it had gone pop because the value's written on it. So I can take my multi-pack of resistors that I purchased and look through this one for a 2.2k resistor, and I would have a spare. But you're not always going to get that lucky, because as soon as you go any smaller than that, the values aren't really written on them. We've got some other ones here. We've got a... oh, that's upside down. Hang on a sec. Let me turn it around. We've got a 623 directly below the chip there. So that's 6, 2 and 3 zeros. So that's 62,000 ohms. So 62k. And then what's that one next to it? 85C. I'm not sure what the C denotes there. I'd have to Google search that. But you get the idea. If you've got some markings on it, you can look it up and you can replace it. And likewise there, that one's just got zeros on it. That means it's a 0 ohm link. So that has no resistance whatsoever. It's literally just a wire. And the chances are that's just being used just to jump a gap across the board, or it's being used as a poor man's fuse. However, coming up to here, you can see here, this boy here, that is too small and has no markings on it whatsoever. So for that one, it's denoted as R213 on the board. However, we've got no idea what rating that will actually be. In order to find that one out, we would need schematics. We would need schematics that we can search for R213 to find out what the hell that is. I mean, if it works, we can remove it and we can measure it. But if it's actually melted and gone bang, then we have no way of knowing. And that's the point where not having schematics will be your downfall. However, again, at that point you have to ask yourself, well, what if I just left it off the board? So what if you did just left it off the board? Well, if it's something that's important, then the board won't work, so you know it's actually going to be necessary. However, there are plenty of instances where certain components aren't actually required. The reason why I've been able to leave capacitors off the board is that a lot of the time, these boards are over-engineered, and some of those capacitors are not actually mission critical. So we looked at our V-core capacitors over here, and we don't need all of those. If we removed one of those from the board, it'd work just fine. Because although that's removing ripple, the chances are this thing will quite happily operate with just a little bit of extra ripple on it, and it'd be just fine. Because remember, we're fixing the laptop, but we don't need it to last the 20 years that the manufacturer intended it to last. Hell, if it lasts a quarter of its lifespan at 5 years, that'll see it through to obsolescence, allowing for the fact that it's already a couple of years old. This one's obviously much older than that, but hypothetically. So you have to think critically and say, ideally we want to replace everything. However, there are certain instances where you have to ask yourself, can it work without this, and what's the penalty for it not having it? Sometimes you've got to find out. If it's a bulk bypass capacitor like this, not having one of these on the board, that could be the difference between it crashing or not when it slams onto load. However, a tiny little ripple capacitor or another small capacitor somewhere else that's just there for ground loop inductance, the chances are it'll live without it. So that's about it. This video is long enough already, but I've given you some rough basics on how to approach on how to approach identifying components for replacement and how you can buy some of these multi-packs to get you started. Because certainly, as far as I was concerned, one of the daunting things was just not knowing what I should try and buy in advance. Whereas with these multi-packs, whenever I come across a capacitor that's blown up, the chances are I'll have a spare one now. So as I mentioned, I bought the 0805 size. I would recommend getting some 0805s and some 0603s. And if you get 0805 and 0603, the chances are you're going to have something that is the correct size and capacity for the one that you've removed from the board. I hope that's helpful to all of you. Thank you very much, and I'll see you all in the next video. Bye for now.